So we're actually moving on to now another chapter, chapter 5, which is on the regularity lemma, which is kind of, you should think of it as kind of an approximation theorem for graphs. Maybe before we even talk about it, let me just kind of mention a sort of approximation theorem that you might be familiar with from real analysis. So here's a thing you might know. So for any continuous function f from, let's say, the interval 0, 1 to the reals. By the way, we're not going to like ever use this theorem. This is just like to provide a bit of context. And let's say I've got some epsilon that's positive. There exists a polynomial p from 0, 1 to the reals such that if I take f of x, the absolute value of f of x minus p of x, it's less than epsilon for all x in the domain, so the interval 0, 1. Is this a familiar statement to people? Does anyone remember like a name for this? Or I think it's like the Weierstrass approximation theorem or something like that, right? Like I said, this is not. Oh dear! Now I've started writing it. I need to figure out how to spell Weierstrass. But yeah, it's something like that. Right? And kind of like the idea is like this, right? You've got some function on an interval, it's continuous. I fix an epsilon, which is a sort of, you should think of it as like a little tolerance, so it's like a little window, an epsilon kind of window around this function. And no matter how small I pick the epsilon, I can find a polynomial that, kind of goes through that window, right? Okay, so, one thing which is like just a standard fact of life is that like, okay, I mean, if I make the epsilon smaller and smaller, then the kind of complexity of my polynomial might get higher and higher, right? I mean, if this function is not itself a polynomial, then like if I make the epsilon smaller, the degree of the polynomial that I use to approximate it is going to get higher, right? You're not going to be able to avoid that. But then there's another kind of thing here that this polynomial, this polynomial depends on the epsilon and it depends on the f, right? So if I just fix my epsilon to be 1 over a million, let's say, but I change the f to make it like super wiggly. So yeah, if I fix epsilon to be 1 over a million, maybe for this f, I can approximate it with a polynomial of degree 1000, let's say. But if I like wiggle this like a billion times between 0 and 1, right, you will no longer be able to approximate with the polynomial of degree 1000 because it goes up and down more than a billion times or something. So your polynomial's degree is going to have to go higher and higher and higher depending on the f, right? So, and this is like, this also seems like a fact of life that should be unavoidable. If I want to approximate something that's really complicated, well, the complexity of the approximation should go up, right? So this is why this next topic is kind of profound. It's because, like, what if I was to tell you that for graphs, if I want to take an epsilon approximation of a large graph, n vertices, no matter how complicated it is, you can find an approximation where the kind of complexity of the approximation, okay, in this case we were talking about polynomials, so it was like the degree of the polynomial. But this will be a little bit different, but basically no matter how complicated your graph is, you can approximate it, get a kind of epsilon approximation where the complexity only depends on epsilon and doesn't depend on how complicated the graph is. Seems like way too good to be true, but it's true. So that's something which is the Szemerédi regularity lemma. Possibly possibly the most profound statement ever proven about graphs. And yeah, so that's what we're going to focus on. Yeah, so is it clear what I'm trying to say here? No matter how complicated your graph is, pick an epsilon, you can approximate that graph. And in fact, you can approximate all the graphs in the world with an approximation where the complexity depends on the epsilon and it does not depend on the graph. Okay. Any questions about that? Any protests? Right? This seems controversial, right? This cannot be true, but it actually is true. Okay. Before we state this theorem, we need some a definition, maybe a couple of definitions. So given a graph G and disjoint non-empty subsets, or actually just disjoint subsets. Well, no, sorry, non-empty. So disjoint non-empty sets A and B in the vertex set of G. The density of, let's say, the pair AB is this quantity. So I'm going to say D AB. And all this is going to do is count the edges from A to B. So if I write this EAB, this is the number of edges with one endpoint in A and one endpoint in B. And then I divide by the size of A times the size of B. So you should think of this as like a kind of percentage of kind of the number of possible edges between A and B, right? Because if I took two sets A and B, if every possible edge existed between A and B, there'd be A size of A times size of B edges. And so this is like a proportion of, proportional to the maximum possible number of edges, how many are there actually between A and B, right? Okay. Okay, so what we're kind of gonna think about is, like, I want to have some sort of a definition that will capture sort of an idea that, like, imagine you've got, let's say the density between A and B is 1/2, let's say. Right, so about half of the edges appear between A, half of the possible edges are there. You could think of, this could happen in lots of ways, right? The edges might be kind of uniformly spread, right? They might be like, kind of look like a kind of random set of edges. Or they could be very kind of structured. Like maybe this vertex is adjacent to everything, and then like, there could be some very kind of special structure between these two things, right? I guess one way you could have half the edges, for example, is like everything here is adjacent to everything here is adjacent to everything here, and there's no edges between, right? That's one way you could have density 1/2. Well, approximately 1/2, or maybe exactly. But like, we want to sort of say, under what, like we want a sort of a definition that will capture the property that it's not superstructured like this, so it's actually kind of random looking edges. So that's something called epsilon regularity. So again, G is a set of vertices, and I've got two disjoint sets. So it's the same kind of setup as there. So for epsilon greater than 0, say that AB is epsilon regular if for any, let's say, A prime, which is a subset of A, and a set B prime, which is a subset of B, such that these sets are not too small, meaning A prime has at least an epsilon proportion of the vertices of A. So the cardinality of A prime is at least epsilon times cardinality of A, and cardinality of B prime is at least epsilon cardinality of B. If the edges really were kind of uniformly spread, right, meaning they're kind of random, if I take any two subsets, you would think that the density between those two subsets would be about the same as the density between the kind of global sets. And that's what the condition says. It's going to say, so the density between A prime and B prime is about the same as for A and B, but the difference is only epsilon. So density from A prime to B prime minus density of A to B is less than epsilon. And you should think of this as the edges are kind of uniformly spread. Up to some like, tolerance like epsilon. Okay. In this definition, you might, one weird thing is that epsilon is kind of, it feels like epsilon might be playing too many roles here, right? Like, I mean, I'm saying that the sets have to be at least epsilon times the A prime is epsilon times A, B prime is epsilon times, at least epsilon times B, and then I've got this epsilon here as well. Like, formally you could define like a delta epsilon regular, regular, and you could have like a delta here, and an epsilon here or something, but like, for all intents and purposes, it doesn't really matter. So we may as well just call them all epsilon. They're just some small kind of quantities. Any questions about this definition? Okay, so maybe I'm going to state the regularity lemma. But we're not going to prove this until next week. So this is the Szemerédi regularity lemma. Okay. You should kind of like, in some sense, think of this as an approximation theorem for graphs. So for any epsilon bigger than 0, and any t, so t is an integer, so yeah, it's a positive integer, natural number, whatever you want to call it. I wouldn't worry too much about this t. It's actually kind of useful for some technical purposes, but Really, the epsilon is kind of the most important part. So for any epsilon greater than 0 and any natural number t, there exists some k naught of epsilon in t. So this is just going to be some natural number. Such that for every graph G, there exists a partition x1 union, whatever up to xk of the vertices of G such that the following holds. So firstly, this number k that we're using for the partition is between t and k naught epsilon t. Okay. So the k. So we're going to think of this partition as being some kind of approximation of the graph. Maybe we can try to make that clearer later what that means. But this partition, you can kind of think of k as being how complicated the approximation is, right? So yeah, the kind of complexity of this thing only depends on this epsilon and t. And like I said, t is a little bit of an artificial parameter. It's useful, but anyway, if we kind of ignored the t, then this really just depends on epsilon. So it doesn't depend on the graph. Okay, a few more properties. Each of these sets has about the same size. So, so the size of xi is equal to number of vertices of G over k floor, or the ceiling of the number of vertices over k. So they're kind of as equal as possible in size. So all but at most epsilon k squared of the pairs xi, xj for I not equal to j are epsilon regular. Actually, maybe that's just it. Yeah, that's all I wanted to say. So about that. So right, so this first condition says the complexity of the partition doesn't depend on the graph. The second thing is kind of a nice property that all of these sets have about the same size. The third thing says that, you should think of the third thing as saying that between any two parts, the edges are they pretty much look like just random edges with no kind of discernible structure between them. The edges are kind of uniform. And you can kind of think of this as approximating your graph by some kind of a random graph. So, for example, okay, in this theorem, the number of parts in the partition is going to be enormous. But let's just sort of imagine you had 4 parts or something, right? Or let's say 3 even. And let's say, the density here was, 1/2. And each of these parts have size n over 3, right? Density, let's say 1/3. and density 1/5, right? Like if the k was 3, like this is the kind of thing you would have is you'd partition the vertices of your graph into 3 parts, where here I've got density, let's say 1/2, and it's epsilon regular, meaning if I pick any not too small set of vertices here, and any not too small set of vertices, I know that between those two sets, I've also got about half the edges. And no matter how you pick these sets, you're going to have about half the edges between them. And then like similarly between these parts, but with different densities, right?
So we don't know anything about what's going on inside the sets then?
That's, yeah, and actually that's part of the reason why we introduced this T, because actually in this situation, if you've got 3 parts, there's actually kind of a lot of edges that you don't know anything about that are sitting in there. But if I force the number of parts to be pretty large, then the edges inside the parts, they start to not matter, as, you know, if you make the T kind of large and then pick the epsilon small, the edges inside the parts don't really matter. But you're right, you don't have any information about the edges within a part. So, okay, so the kind of idea here is we take this graph, which could be very complicated, and we can approximate it by kind of thinking of it as a bunch of blobs where the edges between the blobs are random with certain densities. So this would be like random with density 1/2, random with density 1/3, random with density 1/5. Okay. So it's an approximation of any graph by a sort of multipartite kind of random graph construction. Any questions about that? One important question here is this approximation useful? Like here's the thing. All this profound stuff I'm trying to say about how the number of parts in the partition only depends on epsilon and blah, blah, blah. Like, okay, if I just define a really crappy notion of approximation, and then I just, oh yeah, you can do it with like 5 parts or something. But like, if that approximation can't be used to solve any problems, then there would be no point in it, right? So, I guess the important thing here is not only can you find this approximation, but you can use it to count structures in your graph. So the idea is you take a large, complicated graph, pick an epsilon, which is sort of an error that you can tolerate, you know, that's kind of an okay error for you. Approximate your graph with a random thing, count things in the random construction, and then that will translate back to giving you the right count up to a small error in your original graph. Okay, so let's see how that works. So this comes down. This is related to something called the. I think it's usually called the counting lemma. Okay, we're going to kind of focus on a simple case where we're just counting triangles, but it'll be clear that all of these ideas generalize to counting whatever you want. So I'll just say for triangles. Okay, so let x1, x2, x3 be sets. So disjoint, so pairwise disjoint, non-empty sets of vertices. Yeah, kind of in a graph. I mean, the vertex set of the graph is just going to be the union of these 3 sets. So we're going to be kind of in this situation where, like, the whole thing is partitioned into 3 sets. And suppose that, epsilon is positive. But anyway, so xi, xj is epsilon regular for all I not equal to j. So the three different pairs of parts are epsilon regular. And I need to make an assumption about the density, that it's not, the density between the parts, that it's not like super small. So the density of edges between xi and xj has to be bigger than 2 epsilon for I not equal to j. So then my conclusion is going to be about how many triangles this graph has. So then the number of triangles, well, I can't really say, like we were saying, we can't even say anything about the edges inside the parts. So actually, I'm only going to count triangles with one vertex in each of these sets. So with one vertex in each of the xi's is at least 1 minus 2 epsilon times the density between x1 and x2 minus epsilon times the density between x1 and x3 minus epsilon times the density between x2 and x3 minus epsilon times the size of x1, the size of x2, and the size of x3. Maybe I should clarify that we're counting each triangle once. We're not counting like homomorphisms. We're counting like, unlabeled, yeah. It just turns out to be more natural for this. I mean, if you want to count homomorphisms, just multiply it by 6, right? And then, but. Okay. So the way you should kind of interpret this is, like if this truly was like a random graph where I take x1, x2 and x3, right? And I throw in the edges randomly here with the density equal to that number, whatever that number is. It might be a half or whatever. I mean, whatever that number is, if I randomly put in the edges here with that density, randomly put the edges here with this density and here with that density, you would expect to have, so every possible triangle, there's this many possible triangles, and it would, the first edge would be present with that probability, second edge with that probability, and the third edge with that probability. So sort of up to like a small error of epsilon, we're getting exactly how many triangles we would think we would get. Or, well, so I'm saying at least, but you can turn this into something kind of more exact as well. And actually, there's nothing special about triangles here. Because, for example, what if I wanted to count copies, so induced copies, like what if I wanted to count the number of ways to take one thing here, one thing here, and one thing here, where this edge is here, and this edge isn't? Well, you could count this too, because all I would do is I would say, okay, between these two parts, just like locally kind of complement those edges. Just for every edge between these two parts, take it out, and then if there's no edge, put it in, right? As long as that density wasn't too high to begin with, then the density, once I complement it, won't be too low, and finding like triangles in the new graph would be finding this, or sorry, in the old graph, right? And it will preserve epsilon regularity. That's something you have to check, but yeah. So yeah, like basically, and also if you wanted to count things between, yeah, we'll see that the proof would work if I wanted to count any structure between, let's say, k parts, right? Okay. Any questions about this statement? So that's kind of the kind of shows the utility of this, that like this is actually useful because once I have this partition, I can count whatever the heck I want inside this approximation. And it's going to match up with the original graph. Okay. So we're proving this like counting theorem thing, counting lemma. So, okay, what I'm going to do is first I'm going to look through the vertices of x1. And the thing is, like, I kind of know that like most of these vertices should have kind of the right number of neighbors in x2, but not all of them are going to, right? There could be some vertices here that have no neighbors in x2. We can't really say anything about an individual vertex. But what I'm going to do is kind of throw away the bad ones first. So let's say a vertex x in x1 is bad for x2 if it has fewer than dx1 x2 minus epsilon times the size of x2 neighbors in x2. And similarly, we can say bad for x3. So bad for x3 is similar. Okay. And there will be these bad vertices. But the point is there's not going to be very many of them. Because take the set of vertices that are bad for x2. Imagine that's more than an epsilon proportion of x1. So this is my things that are bad for x2. Well, if I take the edge density of this between this set and all of x2, like I can count. So let's say B1, or B2 is a subset of x1. So this is the set of things that are bad for x2. The number of edges from B2 to x2 is at most, or less than, well, I just, for each of these vertices, count the edges. And for each of them, you're getting less than d of x1, x2, minus epsilon times x2. And you're getting that for everything in B2, so times B2. But this means that if I take the density between x1 and x2, I look at the difference between that and the density between B2 and x2, it's going to be bigger than epsilon. Because literally the density is what I get by taking the ratio of this over that product of the two cardinalities. And that's less than this density minus epsilon. So the difference is bigger than epsilon. But this pair is epsilon regular. So if you have a set, so B2 lives here, right? If I've got a subset of B1, x1, that has where this discrepancy is bigger than epsilon, then B2 has to have size less than epsilon times x1. So by epsilon regularity, this implies that B2 is less than an epsilon proportion of x1. Because if it was bigger, then epsilon regularity says that the opposite inequality holds. So it's by kind of contrapositive, right? This must be small. And similarly, B3. If I take the things that are bad for x3 and call that B3, the bad things for x3 is small. And so I can kind of ignore those things. So I've got these small sets that are bad, but then everything else is good. Now I take one of these vertices that's good, right? So it has a fairly decent sized neighborhood here and a fairly decent sized neighborhood here, where decent sized is at least, whatever this is. And, well, the density, this dx1, x2 is bigger than 2 epsilon. So this set here has size at least epsilon times the size of x2. This set has size at least epsilon times the set of size of x3. So I can count edges between them by regularity again. Because this set is regular, this pair is regular. So I can count the edges. So let's do that kind of properly. So if I take some x that's in x1 and not in B2 or B3, so it's not bad in either direction, then it has at least dx1 x3 minus epsilon times the size of x2 neighbors, which by the way is bigger than epsilon times the size of x2 by our I've erased it now, but the assumption we had that this density has to be bigger than 2 epsilon. So 2 epsilon minus epsilon, I get an epsilon. Neighbors in x2. And similarly, it has at least the density between x1 and x3 minus epsilon times size of x3, which is bigger than epsilon times the size of x3, neighbors in x3. By regularity, the number of edges between the neighborhood of x intersect x2 and the neighborhood of x intersect x3 is at least the density between x2 and x3 minus epsilon times the size of these two sets. And this is now using that the pair x2, x3 are regular, epsilon regular. And I'm also using that these neighborhoods are not too small. Yep.
Is that top one supposed to say dx minus 2 minus epsilon?
Yep. Thanks. And now we can use this to count triangles. Take a vertex that's not bad in x1. There are, so I mean, pretty much all of them have that property, except for maybe 2 epsilon times, so yeah, number of triangles is at least, I've got 1 minus 2 epsilon times x1 choices for a non-bad vertex, or in other words, a vertex that's not bad to x2 or to x3. For every such vertex, to choose I've got this many choices of a neighbor of that vertex in x2, so dx1 x2 minus epsilon times the size of x2. I then multiply by, I've got this many ways to choose a neighbor in x3, dx1 x3 minus epsilon times the size of x3. And then the number of edges between those two sets, like the neighborhood of x, in whatever, in both places, is at least the density between x2 and x3 minus epsilon. Well, yeah. Yeah, so this would be like the size of the neighborhood into x2, size of the neighborhood into x3. So these are kind of like these two quantities. The number of edges is between those neighborhoods is equal to those two things times this thing. So okay, the number of triangles containing a given vertex in x1 is the number of edges between its neighbors. So yeah, I maybe kind of didn't explain that in the best way, but this is the size of one of those neighborhoods, so this is this quantity, that's that quantity, or a lower bound on it anyway. And then this is just this thing here. So I guess I should have said the number of edges between these neighborhoods is just the number of triangles that contain that vertex. And then we sum over all the vertices in x1, except for the bad ones, and you would get this. And this is what we wanted. If you just rearrange it a bit, that's the same thing that we wrote down. Okay. Any questions about that? So for example, you could prove the same thing about, if you had 4 kind of blobs, for x1 to x4, and I wanted to find a k4, I would just do a sort of very similar thing. You might have like a minus 3 epsilon here or something, and everything else looks kind of similar. And then if you want to count something that's not a clique, like I said, just take your kind of regular, your partition between any pair that I want to find a non-edge instead of an edge, you just complement those edges between that pair, then you can find it with, kind of as many copies as you wanted with some kind of error of epsilon, right? Okay, so this is like, quite powerful, right? Any graph I can approximate really well with one of these partitions. And then once I have one of these partitions, I can count whatever the heck I want inside of it up to a good approximation.